Okay. Can we start?
Yeah, start.
So good morning, everyone. So welcome to our CWS seminar today. So this will be our last seminar for this year. So that's. But anyway, we are glad we have Dr. Diego Panici. So who was our CREWW members previously working with us for a long time, but now he's mainly working with the CREWW colleagues, and now but still we work closely, and today is a good opportunity for us to know about his new recent research on the catchment scale process on the water quality in the mixed-use groundwater dominant catchment.
Thank you very much, Albert. Good morning, everyone. As Albert was saying, my name is Diego Panici. I used to be a postdoc here at CWS with Prakash on a project that we worked together, which practically was really prolific. We published so many papers out of just a small project like that. I still can't believe that it was that positively accepted. But I'm really pleased to be here today to talk about this, because normally we'll come here and talk about something that we're doing in CREWW or something from my past research. But I thought this is probably the first time that it works the other way around. Is some of us from CREWW going to work with people in CWS, because this is a project that is led by Pete Melby-Shreve, and he sought some expertise they didn't have in his research team about water quality, and there's also another colleague of mine for environmental social science. So I'm particularly happy to talk about this, and I want to advocate the fact that it would be nice to have more of this exchange going forward, in which we try to seek the expertise from both centres and work together, which worked really nicely in this case. Because again, this is a rather small project, but we potentially have a chance to get a really nice publication out of it, and I will explain all about it today. And it's also kind of a first for me. I worked with water quality before, but never such in-depth analysis. And there's particularly a situation in which we have catchment scale processes, try to understand them using high frequency data. So I'm going to talk about a little bit of background, what is high frequency data, if you're not familiar with water quality data sets, and the flow concentration analysis, which is what we did in this case. The site study that we're working on, the results that we got, and any analysis of the hysteresis. So, in terms of background, we live in a world in which our rivers, our water resources are massively impacted by human activities. We also know that rivers and floodplain are the most important ecosystem, and pretty much half of the human population live around rivers and watercourses. 1/3 of vertebrate species, they live in riverine environments, so we depend on this biodiversity. So if we wipe out the biodiversity, it's going to be probably wiping out ourselves as humans. But what we've done is that we heavily disrupted natural legal functioning, and any extremes have been exacerbated, and many of you have seen work with hydrological extremes like floods and droughts, and are quite familiar with that. So what is the problem there? So what we're observing in rivers worldwide is that wetlands have declined by 75%. It's the highest of all habitats. Freshwater vertebrate population declined by 83%. This is looking like extinction numbers. And 1 in 3 freshwater species are at risk of extinction indeed. And there's many other problems that we can discuss about this, but the focus here is water quality. So water quality is particularly affected by 2 types of pollution: point source and diffuse source. Point source is something that released directly into the channel. Diffuse, if there's not something that is released, for example, from a pipe, that is more wider. For example, a field or a large area. And this here is just to give you an example of how the different processes in a catchment look like. We've got point sources, for example, stormwater discharge, we can have wastewater treatment plants, sometimes we have industrial discharges, something that CREWWs are a bit easy to identify because we see a pipe and we know that pipe there will be a discharge. The really difficult ones are the non-point sources or the diffuse sources. They come from the landscape and it can be from large areas. So it's very difficult to identify what is causing what in a river. For example, agricultural land, you have fertilizers and pesticides, then they leach into the soil and they get transported when there's rainfall events, but we don't know which field, for example, is responsible for something. And we don't have any way that is visible to monitor what kind of fertilizers are being used in certain farmland. Then you have plenty of other different phenomena like urban runoffs. You can have that first flush from roads, for example, contains a lot of pollutants, contains salts, heavy metals, so that they can be transported into the streams. So it is very difficult to understand just by observing some standard water quality monitoring what processes are causing this type of pollution. And this is just to give you an example, right? If anybody have ever been here, this is the River Wye at Simon's Yacht. Beautiful, absolutely stunning scenery, but it is considered as a dead river. So the water quality pollution that is happening in this particular river is so high that it's effectively wiping out the water species that live there. But it's not just the River Wye, of course, though it makes the news. And we do know that the culprit most likely is the poultry industry, because there's a lot of poultry farming, and we see very high level of phosphorus and nitrates. So it's quite easy to relate that to that particular source of pollution. But if you then look a bit wider, the UK situation is dire. So we have that no rivers are in good overall status. So it's something that really makes you reflect for a second that the type of pollution that we have in our rivers is absolutely substantial. That means that, having had a look at this picture here, so that basically no rivers are in good conditions, chalk streams that are groundwater dominated and are rare and are one of the unique features of the southeast of England, they are extremely vulnerable. Water quality can effectively change dramatically the ecosystem status of chalk streams, especially from two components: chemicals, in which algal blooms may form, or there can be other detrimental effects, and sediments. So these chalk streams, they rely on having clear waters that comes from the aquifer, but if you put sediments in it, a lot of sediment, like it could happen in this case, then you start smothering these ecosystems. And that's where our study comes in. So that's why we want to use high-frequency data to try and understand where these pollution sources are and the way that we can then take interventions or do more monitoring or try and enforce protection policies. So high-frequency data is defined as data collected with near continuous frequency. Typically it's sub-hourly. So we're talking about 15 minutes, half an hour, sometimes even 5 minutes, depending on the catchment conditions. To do that, we use multi-parametric sondes. So it's the one over there. It's effectively just a pipe that contains in it different probes. Each probe measures one of the different parameters. It could be many, temperature of the water, for example, nitrogen load, pH, dissolved oxygen, conductivity, but there's plenty more. There's plenty available, but these are kind of the standard in the industry and are normally used by the Environment Agency. They do require regular maintenance, so once a month normally they need some calibration, so you need calibration liquid and go there and do the calibration, etc. But at the same time, they capture events that are otherwise untraceable. Like, this is a conceptual scheme, but sample measurements are very rare and sparse. Normally, we're talking about once per month. And if you go out in the field, you don't go when it's raining, you go when it's nice weather, or at least acceptable weather. So you're likely to get some measurements of the baseline chemical concentration, whereas if we're looking at events, we are basically not capturing anything out of it. But we do know by experience that the majority of pollution events, they come when there's an event. So without regulatory monitoring, going out in the field and sampling, we don't really get much out of it because we miss a lot of these events. And they're very effective so for event monitoring, so rainfall-driven water quality events. That's why we can use that data to work around the concentration-discharge relationship. So if we know the pollutant concentration and compare it with discharge, it can tell us from a broad understanding of where it originated and what originated it. So we have an understanding by comparing the flow and the concentration together of where that pollution came from. Obviously, there will be significant variation of concentration when you vary discharge at the point in space, so we will see that they vary, and sometimes they vary in a very non-linear fashion. And normally what we need to do is we need to isolate the storm events. So the key important thing is the hydrological component before getting into the water quality, which is isolate an event in which you see when there's a rising limb and a falling limb. I think all of us are quite familiar with it, but the clear distinction of when these two start, it basically tells us where we need to start our analysis, the beginning of the rising limb, and when we need to stop it at the end of the falling limb. And that's where hysteresis comes in. So if we see a non-linear, non-one-to-one correspondence between flow discharge and pollutant concentration, then this is called hysteresis. Hysteresis means that effectively you have a loop rather than having a linear relationship. The key concept is that whenever we have hysteresis, it means that the parameters are path dependent. So that the phenomenon that we are observing depends on where it's located in the catchment, whether it's located nearby or where it is far away. So that the hydrological connectivity to the main river or to the river that you are analyzing, they depend on where they're placed in the catchment. In order to do this analysis, you normally need normalization. So you take values between 0 and 1. You just normalize discharge and concentration values by the maximum value for that particular event, because that makes it comparable between event to event. And in case you wonder what is hysteresis, I just put the definition there. It simply says a cyclical relationship between discharge and water quality parameter concentration, which is caused by a lag. So that's the key point, a lag between the discharge and the concentration, meaning that if you have a concentration of a pollutant coming through your flow, through your river, it may not just be in the same time as your flow peak. There will be a delay, or it will be anticipated. And we will see what that means in practical terms. There are two indices that we normally use in hysteresis analysis. The first is the hysteresis index, which is a sum, is the average, effectively, of the concentration on the rising limb minus concentration on the falling limb. So it's basically the average of the values that are between these two limbs. Now, by the way this is defined, if the rising limb is greater than the falling limb, then it means that its hysteresis index will be positive. The other way around, if this is the falling limb and this is the rising limb, you have that the falling limb will have greater concentration than the rising limb, and this will be negative. So the key point here is the hysteresis index can be positive or can be negative, and whether it is positive or negative tells us all the story. The other one is the flush index. This is the difference between the concentration at the flow peak, so when the normalized discharge is 1, minus the concentration at the beginning of the event. Again, this tells us a story. If the concentration is higher at the end, or at the peak of the event, and it is smaller at the beginning of the event, it means that there is pollutant that is being pumped into the river. So there's more pollutant. If it is negative, it means that there's a dilution effect. So there's more water than pollutant. And you can have either. But what we've done for this work, we also introduced a third index, which we call the crossing index, that counts how many times these loops intersect together. Because this is a very idealized loop, but in reality, they actually start making different figure of 8, even more complex. So this has not been done in the literature, so we introduced this as a crossing index. We weighted it in a way that it doesn't account for the number of crossing when they're very small, but it includes when you have significant crossing, meaning that there's a reversal of the process. So these are the two processes I was talking about. Accretion, there's an increase of the pollutant. Dilution, the pollutant actually decreases. But that's process. So one of the indices is telling us what process is causing all of this, which is the flash index. But the hysteresis index is telling us the source distance. If there's a delayed transfer, so the flow peaks before the pollutant does, or if there's a near stream source, so if the pollutant peaks before the flow does. And to give you an idea, this is a real schematic. So you've got, in this case, an anti-clockwise loop in which our hysteresis index is negative and the flash index is positive. Here we have that the concentration on the rising limb is smaller than the concentration on the falling limb. In practical terms, it means that this is your hydrograph and this is your concentration hydrograph. Likewise, if you have a look at the other figures, for this one, here we have the hysteresis index that is positive, flash index is positive, and it means that we have sediment being getting into the stream, but this time is before the flow peaks. Likewise, on the bottom row here, we got when we have dilution, so when actually the sediment concentration decreases, and it follows basically the same concepts there. Anti-clockwise, so the hysteresis index is negative, you have that it peaks the dilution before the flow does, and here is the other way around. And then this is kind of idealized, and I'll show you some examples in a minute that is possible, but most likely you will observe something like this, because in a catchment there's got multiple land uses, it's got urban areas and rural areas, and it's got groundwater, so there's multiple processes at hand. It means that some of the parameters will definitely have a complex pattern, meaning that they have multiple sources that are causing that parameter to have different behaviors. And you can see here is kind of having those weird shapes in the curves. So the main research question that we tried to address for this work was, can we leverage the high frequency data to identify the water pollution sources in catchments where you have multiple sources, multiple land use, and where you've got the catchment characteristics that are very different from the usual ones that we work sometimes here in the southwest. So flashy, but with groundwater. And that's where the science study comes in. So this is part of the Resilient Together project. As I mentioned at the beginning, this is a project that is led by Pete Malby-Shreve, and first time that we've been working together on something like that. It's DEFRA funded project through the Resilience Innovation Program. Some of you may be aware of the one that we have in Devon, like DRIP, and I know Albert. We've been working together on that one. This is part of the same family, effectively. The main aim is to create a smart catchment so that the local stakeholders are able to track what's happening in the catchment using this telemetry that's been applied there. And there's several web packages. If you have more questions, you can ask Laura, she knows a lot better than I do. But one on which is the one I'm working on, is water quality. And it focuses on one specific stream, which is the Picks Brook, which is between Herefordshire and Central Bedfordshire. So there's two local authorities that are interested in that. And we are the research partner, and as I say, he is the PI for the work. So that's the Picks. You can see it's located here. It originates actually in here. This line is not fully red, but that's the Environment Agency stream line, and that's the catchment. In purple, you've got land use that is urban. In yellow, you've got land use that is rural, mostly agricultural. It's a chalk stream, as we said. It's groundwater dominated. So most likely, what we're going to observe is that there are diluting effects, because groundwater has a buffer effect, notoriously, and it flows from south to north. About 40% of the area, roughly, is rural, 60% is urban, and because of this heterogeneity, we have multiple pollution sources, highway outfalls, CSOs, nutrient from agriculture. So, in simple terms, it's a real mess to try to understand where the pollution sources are. So that's why we need this type of analysis. And it's more, but it's quite flashy. It means that, in theory, there's a rapid mobilization of pollutants to get into the stream. Overall, we isolated 18 storm events between July 2023 and May 2025, so we've managed to get a decent amount of data sets. That's some of the hydrological data. Don't be distracted by the fact that the Q5 to Q95 ratio is low. For those not familiar with that, it's the ratio between the highest flow, the highest 5% flow during a year, and the lowest 95% flow during a year. The higher the ratio there, the more flashy the catchment will be. However, normally you would expect something like 8 or more. But in our case, it's slower, not because it's not flashy, but because rainfall events and flood events, they last about 6 hours, whilst these analysis is done on daily flows. So in reality, it will probably be higher. In terms of the results, so that's our data sets just clumped together in a single slide. You've got rainfall on the top. This is the flow, discharge, and we've got ammonium, we've got turbidity, conductivity, and dissolved oxygen. There are a few things to observe here, so that's all the rainfall events. There are some data that we didn't manage to capture, whether the level sensor wasn't functioning or it wasn't made available. One thing that strikes immediately is ammonium. You can see that it tends to have this value as the background value, but then there's a spike that lasts for several months and corresponds to a spike this time of the year. And that corresponds with the summer, meaning that most likely this spike in ammonium is due to the use of fertilizers for farmland. So you see that there's potential for increase overall in ammonium due to that. Now, we don't know that for certain, but that's the main suspect, because it happens at the right time of the year and it's consistent with what you would expect to observe in a river when there's a massive use of fertilizers. Even though there's not many rainfall events there, but we did capture a few, but you will see that in reality it's not necessarily event dependent, the fact that we see the ammonium over there. I'd like to point out turbidity as well. You can see that there's, in some cases, some big spikes, but they don't necessarily match rainfall events. So that means they originated in another way. So it might not have been event originated, but have been released into the stream of some sort of pollutant or some sort of sediment. We don't know. The other thing to notice here, conductivity. If you see where the lines are for the events, you see that corresponding to an event, there's a drop in conductivity. So there's quite a nice dilution that happens all the time. So that's consistent. That means that it is what we want to see for these particular processes. Dissolved oxygen, likewise, it's got some of that. There are some areas in which the data sets are not really good, like this part here and this part there, but otherwise it's quite consistent. But not necessarily as detailed that can tell us all about it. Spike in the summer period, so it suggests seasonal patterns, the weather is raining for dissolved oxygen, and apart from a couple of events, all of those that we captured for the flow, they had antecedent rainfall events. We think that it's because it rained only in part of the catchment, because if we take the interpolated Met Office rainfall data, it actually does show that even for those events that don't have rainfall, it was captured. So we think that where the rain gauge was located, it didn't rain, but it rained in other parts of the catchment, hence the kind of observation that we had. And now, on to very briefly here, because these figures are not going to tell us much, but this is how it looks like when you get flow and the concentration. This is ammonium, and that's stability. You can see some trends there, but without doing the concentration discharge analysis, it doesn't really tell us much about that. We can try and interpret some of them. Like this one is very clear that the peak in ammonium comes after the peak in flow, but doesn't really tell us much about the processes. And likewise with turbidity, we got some interesting information, but we don't really see the full picture. Now if we go on to the next one, that's conductivity here, dissolved oxygen on the right. Again, really interesting stuff, but not really meaningful, not a metric that we can say, yeah, we can see that there's definitely a process going on here. Just see a series of graphs that may be pretty, but not meaningful. So that's why then the hysteresis gives us the real picture here. So that's when we put into practice discharge, horizontal axis, and concentration on the vertical axis. And that's for the 18 events that we analyze, how these loops look like for ammonium. And they're reported on this table, the hysteresis index, flash index, and crossing index. Remember, hysteresis index, when it's positive, clockwise, negative, anti-clockwise. So we can see that in this case, there are some that are quite well defined, like event 18 goes all the way down and back up. Same for event 11, but most of them are quite wobbly, they change quite a bit. You can see that the complexity, like event 9 has got 4 major crossings, meaning that for this particular event, the sources of nitrogen were probably varied. Or in this case, because event 9 says that it's negative and the flash index is negative, means that we do have a dilution in the case. So we don't know what the processes were there, but it was a very complex phenomenon. But all the other ones, they're kind of well defined. Now, if you look at the indices, there's a predominance of HI negative, meaning that anti-clockwise loops. And we also have mostly dilution effects. And complexity is quite balanced. So you have some events that there's not much crossing, the other half of the events is quite complex. This means that for ammonium, we can take this conclusion that there's a quick dilution, so dilution occurs quickly. So you get this runoffs getting into the river and they dilute ammonium quite quickly. The runoffs, they overwhelm the concentration, that's why. And it's unlikely there is actually remobilization of nitrogen from the riverbed. Because that's one of the problems sometimes. You get nitrogen that settles on the sediment on the riverbed and gets remobilized during a flood and then increases and has a spike for nitrogen concentration. This is unlikely to be the case because we see strong dilution effects. And that's turbidity. So I think this is probably the most interesting one for this particular catchment. I wouldn't say it's very complex. Most events tend to follow a loop, and you can see it's kind of the same shape for the loop. However, if you look at the arrows, and obviously you can have a look at the indices as well, they start going in one direction, so they go anti-clockwise, and then at some point, between event 8 and event 9, they switch from anti-clockwise to clockwise. So event 9, clockwise, clockwise, and so on. So that's quite remarkable as a thing. And yeah, we're saying there's a shift from anti-clockwise to clockwise. In the vast majority of the cases, we have accretion, meaning that whenever there's an event, there's probably sediment getting into the stream, so we have more concentration of sediment that we can observe, rather than having dilution, so removal of sediment. And they're normally not complex. The idea that we got is that because this trend means that we have more sediment delivered to the stream before the peak, that probably a new sediment source has developed. And by talking with the stakeholders, there's potential construction sites being built near the stream that are causing that. There's most definitely a surface source mobilization. So because we see that it's accretion all the time, it must be something that gets generated from the surface, gets taken into the stream, and then gets transported. It's not something that gets generated from the riverbed itself. And there's a limited complexity. That's also very interesting because it indicates that likely we're talking about a single source. So we're not talking about multiple sources across the catchment, but likely what's causing this turbidity is one source, or a small number of sources that are located next to each other. Then we got conductivity. So this one, you can see that HI is pretty much positive apart from a handful of events. It's a strong clockwise behaviour, and it's all dilution effects. So we get that it's all negative flush index, which is not a surprise because it means that there's a lot of dilution happening. There's a lot of runoff coming into the stream. So we have that the ions, the free ions into the water, they're actually more diluted. And there's a balanced complexity. So it means that chalk streams are rich in iron. So because they're chalk streams, they've got a lot of metals in it that could be of different origins. But if you add a lot of water, those ions that are free within the stream, they basically get diluted. That's why you always have dilution here. Interestingly, it takes some time to get diluted. So it means that most likely the groundwater is creating a buffer effect, so it's delaying the dilution. Instead of getting the dilution quicker, the groundwater that feeds the stream is delaying that dilution, so it happens after the flow peak. Finally, dissolved oxygen. For this one, we have a strong clockwise behavior, so again, very similar to what we've seen before, and most of them are dilution effects. So you can see that the flush index is negative. It's a balanced complexity, so again, it means that there's multiple sources that are playing in. Again, interestingly, the dilution only occurs after the discharge peaks. Now, if you're familiar with water quality, dissolved oxygen means how much oxygen is available within the water, and there could be a variety of reasons why you have a reduction of oxygen. It could be because there's a lot of sediment coming in, so it's taking place of the oxygen, or there's some organic matter that is utilizing that oxygen. It's hard to say at this stage, but it tells you that there's something going on, and it's most likely coming from multiple sources, because you have some events that are single source, but other events that are multiple sources. It's just a summary of what we say. So runoff flows, they dilute ammonium and conductivity at their offsetting phase, so they work together, ammonium and conductivity. This is interesting, there's a decoupling between ammonium and dissolved oxygen. What it means is that whatever is causing ammonium to behave like that is not causing dissolved oxygen to behave the way it does. So the two processes are separated. That's the really interesting stuff. Whilst ammonium and conductivity, they might be linked, but ammonium and dissolved oxygen, they're separated. And as I was saying, it could be some processing in the catchment, like fast depletion of ammonium. So you have some ammonium storage stays already there, but it gets flushed away very quickly. And then there's oxygen demand because you start having breakdown of organic matter. It's something that we don't know at this stage because we only get a picture of the whole catchment. But with further testing, we can get even to more details to this. The other one is the decoupling between turbidity and conductivity. So again, the two processes are totally separate. So you can tell turbidity is going one way, conductivity is going another way. Basically, this is quite simple. We can say that the surface runoff are driving the sediment into the stream, whilst at the same time the subsurface flow from the groundwater is diluting the conductivity. So it takes longer for that. It's buffering the conductivity. So it takes longer for the ions to be diluted. And if we want to summarize all this information and what's happening in the pigs, so we can say that urban runoffs, so they most likely have an influence on the flashiness, but we don't really see, coming from highway outfalls, large number of salts or metals because conductivity gets diluted all the time. If there was a large component of, let's say, highway salts that are used for gritting, you will see a spike in conductivity, whilst we always see a drop. CSO spills, quite surprisingly, are potentially not a big issue there. Obviously, we're only talking about a year and a few months. There could have been events that, like a dry spill that we're not aware of, but during the events that we monitored, it's unlikely that it happened because ammonium was most cases diluted. So we didn't really see an increase in ammonium. And when there's a CSO spill, ammonium definitely goes up. Groundwater inflow, we saw that that's a very important parameter that really affects all the water quality processes because it has a buffering effect. Agricultural runoffs might not be a big problem for event-based concentration, but they do increase ammonium overall during the year. So you see spikes that last for a few months and then go back down. And most likely culprit for turbidity peaks, some activities that are happening near the stream. We think it could be construction sites. We don't know that for sure, but it looks like the potential responsible for that. So we have more sediment going in, and there's been a switch happening all the time. So in conclusion, what is really important, what we learned about this process is that hysteresis analysis can give us a reasonable understanding of the catchment scale processes. It doesn't tell us the full story, but it tells us that there's different things happening and where we can intervene, where we can put more monitoring in place if needed. There are some clear trends. The turbidity, as I said earlier, is one that is the most striking. So we want to understand what is going on there. So what is causing this turbidity difference? The groundwater buffering is clear, which in a way is a positive thing. It means that it's effectively delaying any effects with water quality, any detrimental effect. So we do know that happens in chalk streams, but it's good to see it on the data as well. And as I was saying earlier, so limited ammonium accretion indicates that perhaps CSOs are not a major issue here. There's wastewater treatment works that perhaps may indicate localized fluxes that might need some monitoring, not necessarily as a catchment scale problem. Next, I know that we're in the second phase now, and there will be some additional work. And what we want to do and what we discuss with the partners is try to increase the spatial scale. So we got now monitoring there's a bottom of the catchment. We want to perhaps start monitoring some sub-catchments so that we do more decoupling. So we've done decoupling between parameters, now we can do decoupling between areas. And we started, myself, doing some GIS analysis to evaluate the flow pathways and land use. Just brought an example that I ran quickly yesterday in QGIS, but it gives you an idea of what are the main parcels of land that are contributing to the flow accumulation. And we may want to increase the measurements within the catchment because we want to kind of capture that sub-catchment scale process, and as part of putting it together, it's also to try and get what solutions can be implemented and what can you work with the stakeholders in there to improve water quality. And that's it. Thank you very much.
Thank you. Good. Any questions? Mohammed, first.
Thank you very much for your presentation. Great work. Have you measured the temperature?
We do have temperature reading,
All right.
for the water. We didn't do any hysteresis analysis for that, but we did have the full set of water temperature.
Yeah, that would be interesting. The pH, usually it's challenging to maintain the sensors.
Yeah, pH requires the monthly calibration, plus pH is prone to drift in many cases. But we didn't have a pH probe here. So this is managed by the Environment Agency, although it's been provided by the Resilient Together. You will correct me if I'm wrong here. But Resilient Together provided the sonde, the Environment Agency maintains the sonde, and the data is available from the Environment Agency website. But they only have ammonium temperature, dissolved oxygen conductivity, turbidity.
So the pH is your sensors or the environment?
There is no pH measurements as far as I'm aware.
Oh, okay.
There might be, we didn't analyse it for sure, but I can't remember if pH is available.
And the dissolved oxygen, that was monitored continuously? Or?
Yeah, they're all the same frequency, 30 minutes for that particular one. We requested to increase to actually 15 minutes because it would be better.
Yeah.
Okay. To have even more frequency.
Yeah. No, that's great. I think the temperature would have some impact on your.
Yeah, so I've done some actually preliminary analysis of the temperature. It didn't show big changes in terms of the hysteresis. But what it showed was that buffering effect stays for temperature as well.
Right.
So the colder water coming from the groundwater aquifer actually buffers the overall change in temperature. So you don't see massive change during the event. But I didn't do a full hysteresis analysis for that one.
Thank you.
That's all right, thank you.
Thanks, Diego. I think I like more about the pics in that 20 minutes than I have in 2 years. Really interesting. I've got 2 points. One is, have I told you about our rain gauge grid, 22 rain gauges that we put in the catchment?
Yeah.
So where you said that you're comparing with rainfall, from August this year we'll have rain gauge data that will enable you to see where it was raining.
Yeah.
If that's relevant. So.
Yeah, the problem with that is that all the data sets I got are up to May.
Yeah.
So
Right.
just before the rain gauges were operational.
Yeah. So and then the other was I'm really fascinated and kind of relieved to hear that there is groundwater making it into the pics. Is that throughout the length of it? And because it has very low flows, doesn't it? When there's no other kind of runoff, it runs very small. So are you able to quantify how much groundwater is getting in? But you definitely do know from these results that there is some groundwater getting in. And is it across the whole length, or is it just at the top of the
That I don't know, because the data that I analyse is only at the bottom of the catchment. I would assume that there's a contribution throughout the length of the pics, but probably varies and it gets higher towards the catchment by the look of it. But I can't tell if it is the real story or not, because the level sensors just tell me that.
Yeah.
I do know that the other ones sometimes do record dry conditions, and they was only doing dry spells, which, you know, it could be an indication that those areas might not be covered by the groundwater table coming up. But at this stage, I don't really know.
Thank you very much.
Thank you.
Other questions? People online?
Yeah.
Yes, one more.
Thank you very much for the
Thank you.
nice work. So I'm quite interested in your result, particularly the tools you use, the index. I wonder how could the catchment manager use the result to help them make decisions about catchment management solution. So the 18 events, right? So you got the one. Have you tried to group them, to clarify, look at to see if there's more clear trends between different the events? Obviously they're very complex, as you mentioned.
Yeah, I haven't actually spoken about that, but we did the correlation analysis between the different indices and the different events, and saw that there was, I mentioned briefly the decoupling effect. That was the clear trend coming out, the decoupling between some of the different parameters, and that tells when you have different processes going on. I haven't done more than that in a way, because what we're observing is catchment scale processes. So the kind of results that you get is what are the processes happening in the catchment and how far away are they from your monitoring point, and if they are further than the flow coming into the monitoring point, or if they are nearer than the flow. That's essentially the type of analysis that the indices can tell you. But there is a consistency between some of the events. I don't have the graph here, otherwise I can show you that there's that correlation between certain events and certain observations with the indices that work quite nicely. And I forgot to mention, we have a paper currently with the Journal of Hydrology under review, and we included that within the paper.
Yeah, so you mentioned that, a few the tasks in the next step. I wonder, have you considered to try, some catchment models, like I think the GIS-based massages, I think were used by the industry to see the detailed process and compare with the result. Maybe something you consider in the future?
Well, if I have more time, I'd love to, but I think it's only like 5 or 7% of my time there. So I'm mostly playing with GIS.
Yeah.
Ideally, if there was a postdoc working on it, can probably do some proper hydrological modeling, so using simple rainfall runoff modeling, or even something a bit more complex than that. The GIS, which was the one that I showed earlier, it tells us where the flow paths are. So what I'm planning to do for this particular part of the project is take that information, overlay to the land use, overlay to the size of the sub-catchments, and see which ones have a contribution, let's say from agricultural land, so that we can expect the contribution from those lands and go there and do some additional monitoring. But ideally, modeling would be the gold standard there, which tells us the exact pathway.
Yeah, I think that should be included in the subject, right? Subject can simulate the kind of processes.
Yeah.
The open source tools might be useful.
Yeah.
I don't know, so probably compare with your, the previous results.
Yeah, I have some experience with other models, like even top model, but I wouldn't have the practical time to do it. that's my main reason here.
Thank you.
Thank you.
Other questions? Diego, the next stage you want to have more sub-catchment scale. So that means you probably will have more sensors.
Yeah.
So
they have 2 more sensors. One that is called eco detection, which is a sort of portable lab that's been installed midway of the catchment, and they have another sonde like the one that's been installed at the end of the catchment that they keep mobile, so it can be moved from one place to the other. So we are planning with the project partner to identify some locations where they can keep it for like a month or a few weeks, and then record some of the events and compare with the overall catchment process.
Mhm.
So it can help us to really identify what's happening for single
Yeah.
and small catchments and try and decouple for each one of them.
Brilliant. And then you try to isolate it 18 events.
Yeah.
So, but have you also looked into those dry spells? So, because this groundwater is maybe there's more
Yeah.
contribution from groundwater during the dry period.
I haven't looked properly at the dry spells. The reason being, with hysteresis, it works really well with a hydrograph.
Yeah, yeah.
But when the flow is kind of flat, you don't really see much happening. You just see the concentration changing, but not the flow changing. So it doesn't have much in terms of the processes, because it's more something must have happened somewhere in the catchment, but not driven by rainfall.
Thank you. Any final questions? So if not, so could you please join me to thank Diego again? Yeah, so this will be our last seminar for this year. So we will be back in January. Thank you, everyone.